All right, so get this. Today, we're doing something really different. I'm really excited about this one. We're doing a deep dive on a large language model, LlaMA 3.
Right.
But we're not just going to, talk to it and see what it says. We're actually going to try to understand how it thinks, how it works, the nuts and bolts, the ones and zeros, the whole shebang.
I like this. This is cool because, a lot of the sources, they kind of just wave their hands at the AI magic, like, oh, it just does this.
Yeah.
But in this case, this particular source, it really goes down to the nitty gritty math, which is, we're not just changing the oil here. We're taking the engine apart.
Yeah. Yeah, exactly. And you know me, I can't resist a good mystery. So our source starts off and it starts dissecting LlaMA 3's structure. And they have this whole section about configuration parameters.
Okay.
And it's things like, think of it like the model's DNA. Yeah. It's like how many layers it has, what's the vocabulary size.
Right.
All these different things.
That's to unpack.
Yeah, it's a lot to unpack, but trust me, it gets juicy. So how do these parameters though, how do these things actually affect what the model can do? It's not like just adding more layers automatically makes it smarter, right? Or does it?
Well, that's the thing. It kind of does. So you can think about our brains, right? We got all these interconnected neurons, and the information, it gets processed in these layers. And, more layers generally means more sophisticated analysis. So the number of layers in this model, LlaMA 3, is going to directly impact how deeply it can think about the information that it's fed, which is pretty wild when you think about it.
Yeah. So we're going kind of deep, but I want to take a step back for a second. Before we even get to the layers, how do we go from English to something that this AI can even understand? Mm-hmm. And that's where this whole tokenization thing comes in, right?
Yeah, you got it. So every word, every punctuation mark, every, comma, period, whatever, all gets turned into a numerical representation, a token. It's like translating English into, a secret code that only the AI knows.
That's fascinating. Okay, so we got our secret code.
Yeah.
But then how does it make sense of the code? And that's where these embeddings come in.
Right. Embeddings, this is where it gets really wild.
Yeah.
Because, see, each one of these tokens gets transformed into, it's called a vector, right? It's just like a list of numbers. And it's not just a random jumble of numbers. These embeddings, they actually capture the meaning of the words.
Oh, no.
In a way.
Really?
Yeah.
So there's a bunch of numbers that represent the word cat.
Yeah.
And the AI knows that means cat.
In a way, yeah. I mean, it's not that it knows cat like we know cat.
Okay.
But it has a numerical representation of what that word means.
That's mind-blowing. Okay.
It is, yeah. And what's cool is this source actually goes into some of the math behind it and how even seemingly simple math is super important to make these embeddings work. They use something called, I think it's RMS normalization. It sounds complicated.
Yeah.
It's really just about keeping things balanced.
Okay, so why is balance so important in this?
Well, okay, so imagine you're trying to judge a singing competition, right?
Yeah.
But one of the singers, they show up with a 1,000,000-watt spotlight and a wind machine.
Okay.
Right? Would that be a fair comparison to, the other singers who just walked out on stage?
No, they're going to steal the show.
Exactly. So normalization, it's like making sure all the singers are on an even playing field so that way no single feature drowns out the others.
Right.
We don't want the spotlight to be the only thing you remember.
Right.
We want to actually hear the singing. So it helps the model pick up on, the subtle nuances of the language, those little details that make all the difference.
Okay, that makes sense. But hold on, how does it know the order of the words matters?
Yeah.
Because you could have the same words, but if they're in a different order, it means something totally different.
Totally, yeah. It's not enough to just know what words are there. It needs to understand where they are in relation to all the other words.
Right.
And that's where positional encoding comes in.
Positional encoding. So that's we're giving each word a little GPS tag.
Exactly. And what's interesting is that LlaMA 2 uses, I think it's ROPE, rotary positional embedding. It's a mouthful, but...
So it's each word is doing a little dance.
Yeah, kind of. Yeah.
And the way it spins and twirls tells the model where it is.
Yeah. It's weird, right?
That's really weird. Okay.
Yeah, but it works. So with ROPE, the model can tell the difference between, the dog bit the man versus the man bit the dog.
Okay.
The meaning is encoded in those rotations.
Okay. So we've got our words encoded. They're in position. But how does it actually understand the relationship between the words? And that's where this attention mechanism comes in, right?
That's exactly it. This is the fun part. This is where the magic happens.
Okay. This is what I've been waiting for.
I know, right? This is cool.
Yeah.
And our source here gets really granular. They're focusing on like the first layer and the first attention head of LlaMA 3 just to kind of keep things manageable.
Okay.
But keep in mind, this is like the tip of the iceberg.
Okay, let's do it.
All right, buckle up. This is going to be fun.
Okay, so we've got our words. They're all lined up. They're doing their little, rope D dance. They got their GPS coordinates. The AI knows who's where, but now what? How does it actually connect the dots and figure out what the sentence means?
Right. So this is where it gets really mind-blowing. Okay, so imagine, right, each one of these words, it suddenly becomes like a detective at a crime scene. They've all got their magnifying glasses out, but instead of looking for clues, they're looking at each other.
Wait, the words are looking at each other?
Yeah, so each word, through its embedding, it's paying attention to all the other words in the sentence.
Okay.
Trying to figure out, okay, how do I relate to these guys? What's my role in this whole story? And that, my friend, is self-attention.
Okay.
It's how LLMs like LlaMA 3, this is how they go from just like a string of words to actually understanding the meaning.
Okay, that's wild. But how does a word even look at another word using math? That seems impossible.
It does, right? It sounds impossible, but that's the beauty of it. Like under the hood, it's really just, you know what I'm going to say, more matrix multiplications.
Of course.
But we don't have to get into the weeds there. What's important is that these calculations, they produce what are called attention scores. So it's basically a measure of how much each word should care about the other words.
Okay, so if we're talking about the sentence like the cat sat on the mat.
Right.
The word cat might pay a lot of attention to the word sat.
Exactly.
Because those two words are very much related in this context.
100%, yeah. And it might pay less attention to like the or to Matt because they're part of the sentence, but they're not as directly connected to the action of cat. Okay, now here's where it gets even cooler. So during training, the model actually wears a blindfold.
A blindfold?
Yeah, it's called a mask.
Okay.
So you can think about it like this. It's like our detective works. They're trying to solve this mystery.
Yeah.
But they can only see the clues in front of them, not the ones that are coming later.
Okay.
It's like reading a detective novel.
Yeah.
But someone ripped out the last few pages.
Why would we do that to the poor model? Well, think about it this way. Think about how we learn language, right?
Okay.
We hear a word, we see it used in a certain context, and then over time, we start to understand what it means, how it fits into sentences.
Okay.
This masking process is kind of like that for the AI. We're forcing it to learn how to predict the next word, but it can only use what it's seen so far.
Okay.
No peeking ahead.
So it's like training wheels for AI.
Exactly. Yeah. Training wheels for AI.
I like it. Okay. So how does it know which clues are the most important? So just looking at all these words, but...
So that is where softmax comes in. So remember those attention scores we were talking about?
Yeah, right.
So softmax takes them scores, which are just numbers,
Okay.
and it transforms them into probabilities. So instead of just knowing that, cat pays some attention to sat,
it knows how much attention. So it might be like, okay, cat is 80% sure that sat is the most important word to focus on right now.
Okay, I'm with you. So it's figured out who the VIPs are in the sentence, but what does it do with that information?
Great question. This is where value vectors strut onto the stage. Remember how we talked about how each token has this embedding?
Yeah.
This vector of numbers?
Yeah.
Well, those embeddings, they come back into play here.
Okay, so it's like each word is bringing its resume to the table.
100%.
Yeah.
Yeah. It's showing off its skills. It's like, this is what I got.
Okay.
And then the attention mechanism, it's like, it's been reading all the resumes. It's decided who to hire.
Okay.
And those chosen few, their value vectors, they get multiplied by those probabilities we were talking about. The ones that say how important each word is.
So it's not just who you know, it's how well you know them.
Bingo. It's like a weighted average.
Okay.
Where the most important words, they get to speak the loudest. And the result of all this mathematical matchmaking.
What is it?
It's a brand new representation for each word.
Okay.
That takes into account its context.
Wow. So each word has basically leveled up?
Exactly.
It's not just a word anymore.
It's not just a word anymore.
It's a word with a whole network of relationships.
It's got its little posse. It's got its crew with it. It's got its entourage. But remember, we're still only in the first layer of this model.
Yeah, it feels like we've been through a lot, and we're only on layer 1.
Right. But that's the thing about these large language models. They're built for depth. So each layer takes those enriched words, those detective words, with their case files full of all this context.
Right.
And it adds another layer of analysis.
So it's like each layer is a new team of detectives, but they have all the notes and the evidence from the previous team.
You got it. And this feed-forward network we're about to get into, this is like their super-powered magnifying glass.
Okay.
It helps them spot even more connections and patterns in the data.
Okay, and this magnifying glass uses something called a SWIGLU activation.
That sounds intense.
Yeah, that sounds intense.
I know, right? I mean, honestly, even for experts, like the exact inner workings of these activations, it gets really hairy.
Okay.
But what's important is that they introduce something called nonlinearity.
Nonlinearity. Is that kind of like when you try to walk in a straight line after spinning around too many times?
That is a fantastic way to put it. I love that, yeah. So imagine you're trying to like, draw a picture.
Yeah.
But you only have a ruler. Yeah. You can only make straight lines.
Right.
But then someone hands you a compass. Suddenly you can draw curves, you can draw circles, all sorts of cool shapes.
So SWIGLU activation is like the compass. It lets it make the curved lines.
Exactly, yeah. But language is full of nuance, right? And these nonlinear activations, they help the model capture that. So this is how it understands things like, sarcasm, humor, all those things that make language interesting.
Okay. Okay, so I'm starting to get the bigger picture here, but we've gone through all these layers.
Yeah.
And we're still just talking about these words as detectives. Like, how do we get to the part where it actually produces language, where it's like spitting out a response?
Okay, patience, my friend. We're almost there. Remember the Hitchhiker's Guide to the Galaxy example that we talked about at the beginning?
How could I forget? We're trying to get it to calculate the meaning of life, the universe, and everything.
Exactly. So imagine we feed the model the first part of that famous line, the answer to the ultimate question of life, the universe, and everything is...
Yes, I'm on the edge of my seat.
So the source actually ran the numbers.
Okay.
They did this experiment.
Okay.
They let those matrix multiplications do their thing.
Yeah.
Layer after layer until they got to the very last one.
Okay.
What happened?
Yeah.
Did it spit out the answer?
Yeah. Is it 42?
It did. So the model, having gone through this whole intricate process, predicted the next token in the sequence. And guess what? That token represented.
No way. It actually worked. It predicted, it said 42.
It did.
Yeah.
That, my friend, is the power of these large language models.
Wow. That's incredible. It really makes you think about, like, what even is intelligence, right?
It is wild, isn't it?
If we can break down something as complex as language into these mathematical operations.
It really is something.
Like,
yeah, and it opens up so many possibilities, right? Because imagine a future where AI can help us, I don't know, write better code or translate languages more accurately,
Right.
Maybe even generate like personalized stories.
Yeah.
Or music. I mean, the sky is the limit here.
It sounds both amazing and a little bit scary at the same time.
It definitely makes you think, right?
Yeah.
But I think that's why, deep dives like this are so important.
Right.
Because the more we understand how these models work, I think the better equipped we're going to be to kind of navigate this future that, they're creating.
Yeah. Well, I, for one, am completely hooked. This deep dive has been an incredible journey.
Me too. And you know what? This is just the beginning. There's so much more to explore in the world of AI. New models, new challenges, and always more questions than answers.
That's what makes it so exciting.
Exactly.
So until next time, keep those curiosity engines running.
Absolutely.
And remember, sometimes the most complex questions can be answered with a little bit of math and a whole lot of imagination.
You're here.